This is the 6B1 section. Our unit is equilibrium. The enduring understanding for 6B is systems at equilibrium are responsive to external perturbations, with the response leading to a change in the composition of the system. We are able to predict the direction of that change by using Chatelier's principle. Chatelier's principle is about restoring balance. Generally, if an external perturbation affects an equilibrium, the equilibrium will be re-established in a direction that restores balance, or in a direction that works against the external perturbation. So for example, if you have the reaction N2 plus 3H2 makes 2NH3 plus heat, and you are at equilibrium, and then you add more to the left side, to the reactant side, the external perturbation has raised the amount of reactants, which will speed up the forward reaction. The forward reaction for a while will go faster than the reverse reaction, and so you will be moving reactants over to products. And so Le Chatelier's principle says the external perturbation was the addition of reactants. The response to restore balance was to make more products. So this would be the reaction graph. Important to note in this statement here that 6B1, that systems at equilibrium respond to disturbances by partially countering the effect of the disturbance. That is Le Chatelier's principle. So here's our N2 plus 3H2 makes 2NH3 reaction again. For the first portion of the graph, we see the concentrations of all three are constant. So that would mean we have an equilibrium. And then somebody goes and adds some reactant. In this case, they add hydrogen. So you can see that the amount of hydrogen has increased. After the hydrogen has increased, the reaction is now going to shift to the right, and so hydrogen will go down. In fact, it goes down at 3 times the rate that nitrogen goes down. You cannot lower the hydrogen and use up hydrogen without also using up nitrogen, because they have a 1 to 3 ratio. As the hydrogen and nitrogen go down, the ammonia goes up. That makes more product, ammonia. And so in this blue area of the graph, we now see the reestablishment of the equilibrium. But notice that the new concentrations of NH3, H2, and N2 are all changed. Because we shifted to the right, the amount of NH3 is greater. Because we shifted to the right, the amount of N2 is less. But interestingly here, the amount of H2 is less than it was right after adding the extra H2, but greater than it was in the initial equilibrium. So we see that the shift has countered the effect of adding hydrogen, but only partially countered that effect. Le Chatelier's principle. Le Chatelier's principle can be used to predict the response of a system to the following stresses. So these would all be good to know inside and out exactly how these stresses can affect an equilibrium. First, let's look at addition or removal of a chemical species. Which way would the equilibrium shift if you added reactant? Well, if you add reactant, as we did in the previous slide, it would shift to the right, because adding reactant creates a stress. You counter the effect of that stress by using up some of the reactant to make product. So then if you added product, you would shift to the left. If you remove reactant, you would shift to the left because that would make more reactant, but not as much as you originally had. You would only partially counter the effect. If you remove product, you would shift to the right in order to replace some of the product that was removed. Okay, the second stress we want to talk about is change in temperature. When we get to 6b2, we will talk about why changes in temperature cause the kind of stresses that they do. At this point, we're simply using Le Chatelier's principle to predict the direction of shift. In order to predict the temperature effect on an equilibrium, you should treat heat as a reactant or a product. In an endothermic reaction, heat would be a reactant. Heat plus the reactant chemicals makes product. So raising temperature would effectively mean you are adding heat. Raising temperature adds heat. Raising temperature adds a reactant, causes a shift to the right. Lowering temperature is basically removing heat. Removing heat causes a shift to the left because heat is a reactant. On the other hand, if your reaction is an exothermic reaction, then what you want to do is look at heat as a product. If heat is a product, then heat would be raising temperature would shift to the left, lowering temperature would shift to the right. Because raising temperature adds heat, it adds a product. Lowering temperature removes heat, it removes a product. Le Chatelier's principle can also be used to predict the effect of changing the volume of a gas phase system. Of course, changing the volume will also change the pressure. If we look at our N2 plus 3H2 makes 2NH3, if we were to increase that volume, the pressure would decrease. In order to partially counter that effect, this reaction would shift left because N2 plus 3H2 is 4 moles of gas and 2NH3 is only 2 moles of gas. 4 moles of gas would help raise the pressure back up. By replacing 2 moles of gas with 4, you increase the pressure. So an increase in volume would lower pressure. You would shift to the left in order to counter the effect. Decreasing volume would raise pressure. You would shift to the right to counter that effect because shifting to the right would lower pressure because 4 moles of gas would turn into 2. So changes in volume or pressure of a gas phase system, you will shift in the direction that more or less moles of gas allow you to fill a larger container or a smaller container. Now it's important to note that if you add a gas that is not part of the equilibrium and not chemically reactive with anything in the equilibrium, that the addition of an inert gas is going to have no effect on the equilibrium. It might change the pressure of the system, but it's not a reactant, it's not a product, it doesn't affect the amount of reactant, it doesn't affect the amount of product. They like to use this question on the AP test, the addition of helium or the addition of neon or some other inert gas. At this point, it's probably good to also interject that the addition of a solid or liquid would also have no effect on the equilibrium, because remember, equilibrium is only going to involve aqueous or gaseous phase chemicals. So if a solid or liquid is part of the reaction, adding or subtracting it does not affect the equilibrium because it's not part of the equilibrium expression. Finally, we have the dilution of a reaction system with water or another solvent. So this would be typically used in a case where you have things dissolved in water. Dilution lowers concentration. In fact, it lowers the concentration of all the species that are in the solution. So by lowering the concentration of all species, we want to counter the effect. So Le Chatelier's principle would predict a shift in the direction that makes more species in solution. This first reaction example is HA makes H plus plus A minus. The left side of the equation has one solute particle. The right side has two, H plus and A minus. So adding water to a weak acid actually increases the degree of ionization because it would shift this reaction to the right. Adding water dilutes the concentrations of the species. Shifting to the right creates more species. So diluting an aqueous solution is a lot like increasing the volume of a gaseous solution. Diluting increases the volume and decreases the concentration. We shift in the direction that has more species dissolved. The second reaction is calcium fluoride solid making calcium plus 2F minus. Now the calcium fluoride solid is not even in solution. It's a solid. So remember, it doesn't affect anything about the equilibrium. But diluting this solution would cause a shift to the right. It would cause more calcium fluoride to dissolve. In order to adjust to reach the new equilibrium, we would shift in a direction that makes more ions in water. Now, if you think about this, what we're really talking about here is we have a saturated solution with some solid sitting on the bottom. If you add more water, more of the solid is going to dissolve. One of the things to consider here is what is the effect on Q. But we're going to table that or postpone the discussion of the effect on Q until 6.B.2. Le Chatelier's principle can be used to reason about the effects the stress will have on experimentally measurable properties, such as pH, temperature, and the color of a solution. Here's an example of MgOH2 solid plus heat making Mg plus 2OH minus. Magnesium hydroxide is actually a popular antacid known as milk of magnesia. But it's called milk of magnesia because it's mostly solid suspended in water. Very little of the magnesium hydroxide actually dissolves to make magnesium ions and hydroxide ions. If we were to raise the temperature, we would be adding heat. Heat would shift to the right, which would make more OH minus. So in other words, heating this solution would cause the magnesium hydroxide to be more soluble. The more OH minus you have, the more basic your solution, and so heating this solution would actually raise the pH. Interestingly, on this reaction, swallowing magnesium hydroxide is actually not too hard on your esophagus because it is not very well dissolved. It has mostly MgOH2 solid, not OH minus in solution. If you think about swallowing a base, that could do very large amount of damage to your esophagus and to your mouth. But in fact, swallowing milk of magnesia is safe because it's mostly solid. It's not dissolved in the water, so the pH is not very high. Interestingly, when it gets into your stomach, it becomes in the stomach in contact with H plus from the stomach acid. And the H plus from the stomach acid reacts with the OH minus to make water. Because it reacts with the OH minus to make water, it removes the product, OH minus, which shifts the equilibrium to the right. So you're swallowing this water and solid magnesium hydroxide, but it's reacting in your stomach with the acid, and so as the OH minus reacts with the H plus to make water, more OH minus forms from the dissolving of the magnesium hydroxide, because taking away a product shifts the equilibrium to the right to make more hydroxide. Le Chatelier's principle can be used to reason about the effects the stress will have on temperature. Here's the reaction: 2NO2 gas makes N2O4 gas plus heat. What is the effect of adding NO2 gas on the temperature? Adding NO2 gas would shift the equilibrium to the right. Shifting to the equilibrium to the right makes heat. So in other words, temperature of the system would go up. What is the effect of increasing the volume on the temperature? Well, increasing the volume would cause a shift to the left because 2NO2 takes up more volume than N2O4, or raising volume would lower pressure. To partially counter that effect, we would shift to the left because 2NO2 would raise the pressure. Le Chatelier's principle can be used to reason the effects of stress will have on experimentally measurable properties such as color of solution. 2NO2 makes N2O4 plus heat is the reaction that we were just talking about in the previous slide. N2O4 is actually a colorless gas. NO2 is a red-brown gas. N2O4, because putting it in an ice bath would be removing heat, N2O4 would be favored if you were in a cold ice bath. NO2 would be favored if you were in hot water. At room temperature, 25 Celsius, you're going to have a mixture of both. So you can see on the right that putting NO2 N2O4 combination in cold water, the color gets lighter in color, and then putting it in hot water on the left, it gets more red-brown. So the color of the solution can actually be affected by a shift in an equilibrium according to Le Chatelier's principle. So here are some Le Chatelier's principles homework: 14.54, 14.56, 14.58, 14.60, and 14.62.